very happy to speak about some recent joint work with my two PhD students, Tomas, Alcalde, and Lorca, Heeney. And if you know anything about these two objects that are in the title, the main result is that we will construct a probabilistic coupling between these two objects, which we think has not been predicted before, so we find that quite interesting. So the talk is composed of two parts. The first part is some recollection of known results, classical results by now. I will talk about the Ising model, the random cluster model, which is associated with the Ising model, the so-called Edwards-Sokal coupling between them. So that's a discrete part of the story. And then there is a continuum part of the story where you take a scaling limit of the so-called Ising magnetization field, and that produces a coupling in the continuum with some conformally invariant objects, in particular the CLE 16/3, which is an object already mentioned in this conference. So that's already known, and after that I will describe our result, and I will start again in the same sort of structure. So I will first give you a new Edwards-Sokal representation for the Ising model. So it will be a coupling between the Ising model and a different percolation model, which has the same features as the standard one. And then we will take a scaling limit, and this will produce a coupling between the Ising field and a GFF. So that's the plan. And yeah, I don't think this has been proposed or predicted, so let's say it's an unexpected connection. And please stop me if you have any questions. So what's the classical part of the story is the so-called Edwards-Sokal coupling. So I will be always talking about, so there will be the discrete part and continuum. In the discrete part, basically everything I say works on any graph. After that, I will assume it's planar and the Ising model critical, so then I will take the scaling limit, but before that, the story holds on any finite graph, which I assume to be connected, and then I have the standard Ising model on this graph, which is just a measure on the plus or minus ones on the vertices. And for this talk, I assume that every edge has a different coupling constants, and that the coupling constants are positive, so the model is ferromagnetic. And in this talk, I will take the point of view of looking at an Ising configuration as a random field or as a random generalized function. So you can think of this object as this configuration of spins as just a sum over all vertices, the spin at the vertex times the Dirac delta. Okay? So that's an object that if you have it, you can apply a test function to it. And then this application is just given by this formula. So this sigma of f is just the sum over the spins and the value of the function at the vertex. So in the end, I will be looking at this object, and I will be taking scaling limits of that, and it will produce some conformally invariant fields. That's clear? All right, so what's the random cluster model? It's a percolation model, so now the state space is just 0, 1 to the edges. So on every edge, I have either an open edge, which is a 1, or a closed edge, which is a 0. And the measure looks almost like the Bernoulli percolation measure, so there is parameter p, which is between 0 and 1, and it relates to the coupling constants by this formula. So 1 minus e to the minus j. And then for every open edge, I have a p. For every closed edge, I have 1 minus p. And the difference is that there is this reweighing factor 2 to the number of clusters. And the cluster is just a connected component of this configuration thought of as a random subgraph of my original graph. And just the technicality that isolated vertices are also counted. Okay, isolated vertices are clusters as well. And so this model was introduced in the 70s. I checked it today again by Fortan and Castelline as a generalization of percolation. And they had some formula which relates this model to the Ising model, but it was just a single formula apparently, and then it was extended to a full coupling by Edwards and Sokal almost 20 years later. So that's why I call it an Edwards-Sokal coupling, not an FK coupling. So the coupling is as follows. If you sample this percolation configuration, given this configuration, now you sample independent coin flips for every cluster, and you assign the spin given by the coin to every vertex in the corresponding cluster. This gives you a spin configuration on the graph, and that's distributed exactly as this Ising model here. Okay, with these J's, and the relation is given by this formula here. So that's a very nice property. So, for example, it leads to this formula, which gives you a way to translate Ising correlation functions, which are basically the main objects of interest in the Ising model. You can translate them into connectivity probabilities in this random cluster model. So what is that here? If you take any subset of vertices, A, and you look at the product of spins and that expectation under the Ising measure, it will be this random cluster measure of some event. And the event is defined in this way. So it's an event such that every cluster of the configuration contains an even number of vertices from A. Okay, so this may look a bit mysterious, but if A is just 2 points, then it means that this event just becomes the event that the 2 points are connected in the cluster. And this is basically a direct consequence of this lemma. If you think about it, if you just look at the product of spins, an expected value of that, there are 2 possibilities: either they are connected or not. If they are not connected, then the spins are independent. So this completely cancels out by this coupling. And if they are connected, that they have the same spin. So the product is +1. So you have +1, and then this happens on the event that the vertices are connected. So you get this formula of Fortuyn and Castellan. That's the formula that was in the first paper. So it gives you a way to study correlation functions in a geometric way by looking at the percolation process. Okay. So for example, this is a realization of both of these models. On the left, I have an Ising model. I didn't specify boundary conditions in the definition, but mostly I will be talking about plus boundary conditions, but I could also talk about free boundary conditions. So I assume that I have a planar graph, and on the boundary everything is a plus. And then the corresponding percolation configuration could look like that, for example. And actually, this coupling goes both ways. Okay, if you give me something like that, I toss coins, and then I can produce a configuration like that. So here the difference is that the cluster of the boundary will always get spin plus, not plus or minus with probability 1/2. But that's the only difference with the coupling for free boundary conditions. But the coupling also goes the other way. So if you sample first the Ising model, then there is a local way of recovering this random cluster model, which is very simple. Basically, you take an edge. If there is a disagreement, then you never put an open edge there. And if there is an agreement of spins, then you toss a coin, and the coin has this probability P. And if the coin is heads or success, then you open the edge. And if it's not, then you keep the edge closed. And basically what does the Edwards-Sokal coupling say is that, okay, I can start with the Ising model. I sample this percolation model on top of that. So I'm adding some randomness. And the property of this randomness is that if I condition on a realization of this additional randomness, the Ising spins become uniform on some subspace of your space. They become uniform on the space where every cluster gets the same spin. So there is this uniformity. So basically, I'm just saying here that if you have a hypercube, a uniform measure on a hypercube is just IID. Okay, so that's a property that is basically essential for this to work. I'm saying that because I will give you a new coupling which has the same property. Okay. All right. So once you have that, you can rewrite also the Ising magnetization field. So this was first proposed by Federico, who is here, and Chuck Newman. So what you can do is you can rewrite this random generalized function using these clusters that you have. So that becomes just this formula. So you have a sum over all clusters in your random cluster model, and each of them gets a spin. And then to each such cluster, there corresponds some measure, okay? I just gather these delta functions into one measure, which corresponds to a single cluster. So that's a geometric representation of this Ising magnetization field, okay? All right, so there is something in planar statistical mechanics which is called duality, and I will at some point mention it in this new coupling as well, so I want to have a picture for that. So if you have a bond percolation model like that, you can always define its dual configuration, which is a configuration on the dual graph. So a dual graph has an edge between every two faces of your original graph. And the rule is that if your original configuration has an open edge, then the dual one has a closed edge and vice versa, okay? So these edges never intersect. And by this rule, having this pink thing, I can define the blue thing, and I call it a dual configuration. And the property of the random cluster model is that it's self-dual in the sense that if you look at the dual configuration, it will also have the law of the random cluster model, but with some different parameters maybe. This will not be the case for this new coupling. The models on the planar and the dual graph, they will be completely different. And what you can do is you can study this whole configuration sort of geometrically. You can draw these loops on the graph, which is called the medial graph. Okay, and these are basically the loops which trace the boundaries between the pink and the blue, so the primal and the dual configurations. And what's known about this object is that at the critical point, on the square lattice, say, we know what the critical point is, what the j's are. I mean, if you put all j's equal to some constant on the square lattice, you can tune that constant to be critical, and there is lots known about this model. For example, it was proved by Kempinen and Smirnov, there's a typo here, that this full collection of loops on the medial graph converges to this conformal loop ensemble, which is called CLE 16/3. So you define the CLE for kappa between 8/3 and 4, I think. So this is bigger than 4, and this has a difference with the difference between this and the kappa between 8/3 and 4 is that this thing is self-touching. All these loops have touching points, and they also touch the boundary. Okay, so that's a geometric difference. Okay, so having all these results, this representation of the discrete magnetization field, all these scaling limit results, one can ask can you combine these things together? And this was done by also Federico, Christoph Gerban, and Chuck Newman in a very nice paper. So what they proved is that if you take this critical magnetization field, so you fix some domain in the complex plane, say, a continuous domain, and you approximate it by a lattice with a small mesh. So I define this approximation of the domain by d delta. And now you take delta to 0. You look at the critical point, the magnetization field as a generalized function. You have to rescale it. So what you rescale by is, okay, there's this delta to the power 15/8. So basically this is delta to the power 2 minus 1/8, okay? 2 comes from the fact that I'm summing of the number of points here is like is the mesh size 1 over the mesh size squared, and the 1/8 comes from the 1 point exponent for the Ising model that was computed rigorously. So that's why you have this 15/8. So this is the right object to look at. So if you have this scaling, you can hope for something non-trivial in the scaling limit. And what was proved in this paper is that this actually converges in some Sobolev space of generalized functions. Actually, the index in that paper is -3, then this was later improved by someone, I forget who that was, but to -1/8, and that's the optimal index. And moreover, the scaling limit is compatible with this geometric representation. So that's the point that I would like to talk about also later. So you can write this field as a sum of basically signed measures. Okay, there is a measure. So there is the scaling limit of the clusters of the random cluster model. Their boundaries are given by these loops from CLE. And each of these cluster measures in the discrete converges to some measure supported in this continuum cluster. And these measures we can call mu C, and the C runs over all clusters of the CLE 16/3. And then each of them comes with a sign which is independent, it's plus minus 1. So here it's an infinite sum, so you have to make sense somehow of it. And one way to do it is you can organize the clusters by size and then remove all very small clusters and then include more and more small clusters. And then this converges to something, and you can define this, you can basically make sense of that infinite sum. I'm saying here just that the CLE is a conformal invariant object, so it has infinitely many loops, okay? So the sum becomes infinite. And all these measures are finite, and yeah, there are these signs here. So I actually don't know if there is a question if this actually converges without the signs. This will be an infinite measure, or not clear?
Probably not.
Okay, probably not.
Because of the regularity, no?
Yeah, I think, yeah.
A measure.
Okay. So that's a result that was the inspiration for us. And here I will talk about our approach. So I will spend some time in the discrete trying to convince you about this new representation. And for that, I have to talk about even subgraphs. So an even subgraph is a graph which has an even degree at every vertex. And for the purpose of this talk, which may be confusing at times, but I don't think there is a better way to do it, the even subgraph has to be on the dual graph of my graph, okay? I will show you a picture what I mean by that. So, okay, so a picture is like that, for example. If the black graph is the primal graph, then an even subgraph will always be a subgraph of the dual graph. And this one has an even degree everywhere, so either 2, 4, or 0. And what I wanted to say is that this thing appears also in other branches of mathematics because it has some nice algebraic property. It's actually called a cycle space. And it's a linear space over the field of two elements where the operation of addition is just XORing, so there's symmetric difference. And the point here is that a symmetric difference of two sets of even cardinality is always of even cardinality. Okay, it's the only thing this is saying. But it's a nice property that you can use for computations and other things. But okay, so there is this classical thing which is called the low temperature expansion of the Ising model, which is basically assigning to every configuration of spins which live here on these black vertices. So blue for me says minus and white is plus. So I can draw the boundaries between pluses and minuses, and this will always be an even subgraph of the dual graph, because I have to change the spin an even number of times around every vertex of the dual graph. And if you look at the measure of the Ising model, this measure induces a measure of these even graphs, and it's a very simple measure. So it's proportional to the product of some weights for every edge on in your graph. And this weight is just exponential of -2 times the coupling constant. So this is very easy. And okay, the case j equals 0 corresponds to the uniform even subgraph. J equals 0 is just independent spins. So if I color my vertices independently, plus or minus, then if I look at the boundaries between pluses and minuses, this is just a uniform even subgraph of the dual graph. All right. Sorry for changing the convention of graphs, but okay. So what is a current for me? A current for me is a pair of sets, or it's a set of open edges which has two different types of edges, basically. One of them is called even edges, and one of them is called odd edges. And the property, which is also confusing, is that these odd edges must form an even graph, okay? These odd edges for me will be here in this picture, the solid edges. And they have to have the property that around every vertex there is an even number of them. And this name comes from some expansion of the Ising model partition function. And okay, there is a reason for this name. So the odd edges form an even subgraph, and the even edges just live outside of the odd edges. They have no particular structure, and here they are these dotted lines. And I distinguish between a cluster, which is a connected component of everything which is red, and an interface, which is a connected component of everything which is solid and red. Okay? So that's a current for me. This even subgraph plus something else. And there is a natural probability measure on that, which comes from this sort of low temperature expansion plus an independent percolation model. Okay, so that's basically that measure here. If you look at it, there is a weight for every edge in the odd part of the current, which is the same as before, this x, and there is this percolation part for every edge in this even part. I have a rho, and for everything else, which I think of as empty, I have 1 minus rho, and rho is something which looks weird, but it's actually, it has a very nice property, because you can rewrite it in this way. So I will keep this thing here. I will keep this formula for later. So the probability of a current measure of a given current is proportional to the product. So for every odd edge, I have this sinh. So this is just a reparametrization of the formula above. And what I've done is also I divided by this 1 minus rho e to the power of all edges, right? Because here I don't have a weight for the edges outside of omega. The weight is 1, which means I sort of rescaled that weight over there. And if you do that, you can see that there is a parametrization of these weights, which is through these hyperbolic functions, which looks exactly like that. So there is a sinh for every odd edge, and there is a cosh minus 1 for every even edge. And if you know the duality for the Ising model, this J star is just the dual parameter of the original one. This is called the Cramer-Spanier duality, but that's not important for me. And if you also know another definition of currents, which is from the 70s, which is more popular, the object I'm looking at is just, you take this original definition of a current, which is just it's a function on the edges which has natural values. You just project these natural values to 3 possibilities, either 0, even, non-zero, and odd, okay? And this will produce these 3 types of edges. If you do that, it's the same model. It's just more convenient for me to talk about this model, okay? So because the only information that is relevant is actually if the edge has an odd value, or if it has an even and non-zero value, which is encoded in this measure exactly. Okay. No questions? So, if you think about it, then you can combine these 2 things. The interpretation of this measure on the even subgraphs as contours of the Ising model, and you have this following coupling. So if I have an Ising model on my primal graph, which now is the triangular lattice, which is not wrong, sorry for that. I draw, okay, so here again the minuses are blue and the pluses are white. I draw the boundaries between pluses and minuses, and on top of that I sprinkle this red percolation process, which has some fixed probability, and this configuration will be a random current. Okay, there is a coupling between an Ising model and the random current, and I will use that to sample the Ising model from some percolation process, which will be defined using random currents. Okay.
So just
yeah.
So the omega 1, omega 2 here is different from the notation here, right? Here is like even odd, and the next page you have was the
next page.
So here omega 1 is the contour, omega 2 is from percolation.
Yeah.
The previous one, here omega 1 is the odd one, and omega 2 is the even one. Is that?
It's the same, so they play the same role. I mean, omega 1 is the odd part of the current, which is distributed like a contour configuration of an Ising model.
Okay.
And then on top of that, there is the percolation process. And this lives on the dual graph. So if you start with the Ising on the primal, the contours are on the dual, and then you add percolation to that thing. And this is my current model. So there is no difference between slide and this one and this one. Okay. Okay, so what do you do with currents? You add them together. So it's a bit, maybe if you don't know it, it looks random, but there's some property of the product measure which is very special. Okay, so how do you add such two configurations? Is that there is this table of addition here. If I have 0, 1, or 2 value, then okay. If I add 0, 0, then it's 0, 1, 0 is 1, 1 plus 2 is just an odd value, so it becomes 1, and so on. And if you think about sets of edges, if you have two currents, you XOR these odd parts. This will be the odd part of the sum of the two currents, and the rest is just, the rest that remains will be the even part of the sum of the two currents. Okay? And maybe I draw this table here as well. I want to give you one proof today. I don't know if I will have time, but okay, so that's for later. And why do you do it? Because there is something called the switching lemma in the double random current model, which is a very powerful combinatorial tool to study correlation functions of the Ising model. It has been used in many places, and it has been used to derive all these most important results about the Ising model. Here is a list. So the model was introduced by Griffiths, Hurst, and Sherman in the 70s, but it was popularized by Michael Eisenman. And probably it's the most important representation of the Ising model to study its correlation functions. And this is definitely not the full list of all these results. I will not talk about the switching lemma today. I just want to give you a proposition that I proved at some point, which is the following proposition. This is the double random current measure. So it's the measure, if you add two currents, I was asking myself this question, what becomes of this measure if you have this representation in terms of these cinches and coches? And I realized that this new measure has a very simple formula, which looks basically like the previous one. There is a weight for every odd edge in the sum of the two currents, and there is a weight for every even edge in the sum of the two currents. But there is still some combinatorial factor in front, and this combinatorial factor counts something, and it's the number of even subgraphs of my set of open edges, okay? I have this current, which is the odd and even. The whole thing is open edges, and I look at this number of even subgraphs of that thing. And that's the formula that you get. And I claim that this is basically enough to have an alternative representation for the alternative FK or Edwards-Sokal representation of the Ising model. But let me try to convince you why this formula is true. So basically what you do is you use this formula for the single measure, which is here.
So can you recall what is P omega here?
I'm sorry, P omega is the power set of omega, the set of all subsets. This is a notation from university. So yeah, so it's just a subset of the open edges which is even. Okay. So what you do is you do the following observation: is that this formula has two parts. If you can still see it, maybe not. It has this sort of energetic part, which is the weights, and it has this entropic part, which is this combinatorial factor with counting something. Okay? So I want to do a computation which sort of splits these two contributions when I do it. And the point is that, if you add two currents, the weights get multiplied, right? Because it's a product measure. And then I look at the result, which is the sum of two currents. I fix a configuration, and I look at the value that it has. And I want to see what is the weight for that value. And I want to sort of distinguish the cases that this value was produced, in the way it was produced from two currents. I want to see the information whether the first current gave an odd value or not, okay? Or even. So this is the information I want to split the computation into. And so basically then you realize that, okay, so first of all, there is this simple case where the sum of two currents has an odd value. Okay, so if this is omega 1, say, and this is omega 2, and then if I know that the sum of the two currents has an odd value, and I keep the information that omega 1 was odd, I have only these two things, which as a sum give me the energetic contribution, and the weight is just the weight of a zero value of a current and a weight of a non-zero even value. So if I want to be, I can also have this formula like that. So for every edge which is outside, I have weight 1. Okay. So for this case, I just get what? I get the product of an odd part from omega 1 and the weight from 0 and from 2, which is what? Which is, the odd part is from here, so that's sinh. So these squares will give me a sinh. Okay, now I made a small mistake.
I think they probably did.
Okay.
Is if you use the blackboard a lot, you can put lights on and take the slides off.
Say it again.
So it's possible to take the slides off if you want to use the blackboard a lot.
Where's the light? I want the slides on, actually. I want this formula as well. So I just want to say that, you know, from the squares I get the weight, which is a product of this guy, and the sum of these two things, which is sinh times cosh. And that's the one which is in the formula. So that's easy, and this is the same. There is a symmetric situation if omega 1 did not contribute an odd part. And this part will have the same weight because it's symmetric. So there are two cases which have the same weight. So after all, I will just have to count these two cases because they have the same weight. I will be just counting. Okay? And there is the more complicated case where you actually use the property of these weights, is this one. So if I know that the sum is even, then I have two possibilities. Either my first current contributed an odd value, and then the other one also has to contribute an odd value. So that's only one thing, and that's just the product of singes. So it's sinh squared. It's correct, right? Yeah, and that's the value of the weight there. And there is another case which is composed of three cases actually, where I have an even value in the sum, but the first current contributed did not contribute an odd value. And if I sum all of these cases, it's the following. So these are symmetric, so it's a weight 1 times the weight of a 2, which is from this measure cosh minus 1. So I have twice cosh j star b minus 1. And then I have to add this one, which is cosh minus 1 squared, because it's twice a 2. And if you do the computation, it's just cosh j squared minus 1, and that's sinh squared. And here is the magic that happens in this, the magic of the double random current is that these two weights are the same. So basically, if I know that the sum is even, the two possibilities for the first current are equally likely, okay? And if I know that the sum of the currents is odd, I have the same property by the first computation. So if I know the sum, to recover the odd part of the first current, I just have to sample a uniform even subgraph. All contributions have the same weight. It's a uniform measure. So that's the property that we wanted to have. There is a uniform measure conditional on some randomness, and that randomness is this double random current model. Okay? Any questions about this? So this gives rise to that combinatorial factor in front. Actually, you can compute it, and it's a power of 2. It's a very easy computation using this this representation as a linear space over some field. And then if you plug in that formula here, your new formula looks sort of like a FK2 random cluster model, but it's actually different. Okay, there is this 2 to the power of clusters. Yeah.
So this formula tells you the XOR Ising model, and then this thing allows you to flip independently at each thing if it's like plus plus minus minus or plus minus minus plus. Is that how you see it?
Yes. That's a different way of saying the same thing. So, but now we have to be careful what it means that the odd part of the first current is a uniform subgraph of this double current. It just means that if I assign spins uniformly at random to the complement of the double random current, you know, this dual percolation configuration, and then take boundaries, these boundaries will be even subgraphs of my original double random current, and they will have the distribution of the boundaries of a single Ising model by construction. So my percolation model is not the double random current, but it's dual complement, the dual configuration. Okay? Because anyway, I started with the Ising model on the primal graph. My double random current was by definition on the dual graph. So if I want to have a model which gives me this FK Edwards-Sokal coupling, I have to somehow go back to the primal lattice. So I just take the dual complement. Okay? So the model is double random current, but the complement of that in the dual graph, you sample spins independently at random, you get an Ising model. So it's a new FK random cluster or Edwards-Sokal representation of the single Ising model. Okay, so I have how much time? 10 minutes or 12 minutes? 20 minutes, okay, most. All right, so that's the discrete part, but so that's what I just said. You sample this double random current on the dual. You look at the configuration on the primal, which is the 1 minus this configuration. And this percolation process has the Edwards-Sokal property for the Ising model on your primal graph. Okay, so there is a problem with that it has no FKG, which is a positive association, but we can handle that at some point. I will come back to it. And there will be some upcoming work with Diederik van Engelenburg and Lorca Heeney, where we will generalize this to non-planar graphs. Because this is only for planar graphs the way it's constructed, but there is a way to do it for non-planar graphs, which happens to be the same in the case when the graph is planar. And we think that this representation has potential applications for other problems, and it's, so we are excited about this representation.
So is the dual percolation on higher dimensional faces then?
So it will not be defined like that.
Okay.
It's a different definition. Okay, so this is not the whole story, because there is this thing called bosonization of the Ising model, which is a mapping between the XOR Ising model and some dimer model, which converges to the GFF and so on. And there is a continuum story that, for example, Roland knows a lot about. I will just mention a few properties of that in the discrete. So there is this XOR Ising model, which is a pointwise product of 2 Ising models. And what you can actually get from the switching lemma, which I did not introduce, is that if I have this double random current model on it's a percolation on the dual graph, and now I assign spins at random to this one, not its dual, then the law of that will be that of the XOR Ising model. So I have a percolation model which has very different properties when you look at the primal version of the dual. The dual gives you a single Ising, the primal gives you single Ising, and the dual gives you XOR Ising, which is a pointwise product of 2 Ising models. And if you think about the construction of the double random current measure, you look at its odd part, so the even subgraph, you think of it as boundaries of some spin model, then this will again be XOR Ising model, but this time on the primal graph. So this double random current has a coupling with XOR Ising model both on the due and the primal graph. I know that this is like, probably you're not following already, but so it took me 5 years or more to understand all the. Anyway, so that's the one coupling, but that's not everything. There is a height function associated to it. I just want to define the height function, and then at some point, maybe I state our result. So the bosonization part is about a mapping to a height function, because height function should converge to the GFF, and that should be the free boson, and that's the bosonization part. So there is a height function associated to all these models. So you start with a double random current model, and you cause these spins for every cluster, which I said now are distributed like the XOR Ising model. And what you then do is you define a height function on the faces, such that if I have a minus for a cluster, and I cross this solid edge, which was the odd part of the current, then my height function in this case increases. No, this is a plus. So the height function increases from outside to inside, and so on. So these are two pluses, and if I cross one of these solid edges, I increase. And if the inside one had a minus, then I would have this decreased. So the height in the center would be 0. So that's very natural. So it's like independent coin flips, and you have some height function which goes up and down. But there is some caveat, which is that the coins belong to clusters, not interfaces. Okay, here I have two interfaces, which are the odd parts, and it could be the case that they are connected by an even edge, which means that now they belong to the same cluster. And in that case, if I cross from the outside and I encounter a different interface from the same cluster, I must go alternatively. I go up and down, up and down. There is no randomness then. So that's a definition which may look strange, but it's very natural if you look at some timer model associated to it and so on. So we defined this with Hugo at some point, and we proved that it converges to the GFF. So what's the GFF? I mean, probably everyone knows, but it's just a Gaussian field. Suppose you have a domain in the plane, you have the Brownian motion field on the boundary, say, and then you do the Gaussian field whose covariance kernel is given by the 2-point function, by the Green's function of the Brownian motion. It's a field, it's not a function, as we know, conformally invariant. Very important. And it has this beautiful structure. I think, okay, a value is here. I think this is one of the most beautiful things I have seen in probability. So there is this function, there is this random field which is not a function, but you can define level sets of this thing as if it was a function, and it all works out. So you can talk about level sets of something which is not a function. And what are these level sets? I will just give you a heuristic because the definition is a bit technical. So what you do is you have your domain and you fix two values A and B, and then you sort of, the value at the boundary is 0, and you explore the values of your field from the boundary, and until they reach value minus A or B, you sort of keep exploring, and they reach the value, and you sort of encounter a loop where the value is reached, and every loop will have either, on the boundary, the value will be either minus A or plus B. So this follows from the definition, which I'm not saying here. And the definition is through some Markov property with the Gaussian free field. So the property is that inside each such loop, the field is independent of what's outside, and its value is basically, the value on the boundary is equal to a constant, which is either B or minus A. So this is, I find this amazing that such a thing can be defined. And yeah, there is lots of known about this object. It's defined if and only if the sum of these two gaps is big enough, with some boundary value lambda, which is the sort of height gap of the GFF, which is some special value computed by Schramm and Sheffield. And yeah, so I will call L minus AB the collection of loops, okay? So the set is just the set which is connected to the boundary between the loops, and so that's A, and L will be the loops which are the boundaries of these holes inside the domain. Okay, so why am I saying all of that? Because I want to tell you what the theorem is, and I don't know if I will make it there, but okay. So there is a very famous coupling between these sets and the GFF, so it goes back to Miller and Sheffield. So if you take a particular value of this gap, which is symmetric, so A is equal to B, and is equal to 2 lambda, you can sample this collection of loops, and they will have labels, so labels are the values, and in this case the labels will be independent, so they will be independent plus or minus 2 lambda. And you can sort of try to approximate your field by repeating this construction inside every loop. So you sort of do a nested version of that, and you just record the values of this random walk that you have. It either goes up or down. And what they proved is that in the limit this will be a GFF. So it's also amazing. No? Like the GFF apparently has some discrete structure. No? It just jumps by these height gaps, and then you can look at it as this branching process. And with this what's the word? With the structure of the parent of a loop is just the loop that surrounds the loop. Okay, so that was the same thing as in EU and stuff. Okay, so this is a very nice result. I'm just saying all of that because we have a similar result for these double random currents, okay? And to state it, I have to define what an outer and inner boundary is of a current. So suppose this is again the current, the red thing, and the outer boundary is some line on the dual graph which surrounds it. It's very close to it, and the inner boundary is inside. And the difference between the outer boundary and the inner boundary is that you can have many inner boundaries, okay? And only one outer boundary. The inner boundaries sort of trace the holes inside your cluster. So the yellow and the green. And what we proved is that, okay, you have again a domain, critical double random current model, which corresponds to the critical Ising model. You look at the scaling limit, and you have the following convergence. This height function that I defined converges to the GFF times some explicit constant, which is 1 over 2 square root 2 of lambda. And it's the same constant that you get from any convergence of any dimer model to the GFF. If you have a dimer model converging to a GFF, it will always converge to the same multiple of the GFF. And yeah, there is a dimer model underneath, so that's no surprise that we get the same constant. The outer boundaries of the clusters converge to CLE4, which is the same as the loops of the two-valued set with values 2 lambda, or minus 2 lambda and 2 lambda. And then there is something different which happens inside. So if you go inside, you look at these inner boundaries of clusters, and they will converge to a two-valued set again, but it will have not the gap 2 lambda, but it will have the gaps 2 lambda and 2 square root 2 minus 2 lambda. So if you add these two together, so the sum is important. So the sum is 2 square root 2 lambda. Okay, it's different than the previous one. For the CLE4, the sum is 4 lambda. For this one, it's 2 square root 2 lambda. So this set will look differently, and it will not be the loops will not be disjoint and so on. And yeah, and the picture repeats in every hole. So this is a nested picture, and I will give you a figure for that because this is a mouthful of words. So that's the picture. The field converges to the GFF. Now the external boundaries are blue. So that's a CLE4. And inside these internal loops converge to this two-valued set where the sum of gaps is 2 square root 2 lambda. So it has the property now that these loops will touch the boundary of the domain. And they will actually touch themselves. And the labels are not independent anymore. The labels are actually such that if two loops touch, they must have a different label. And this is all that we proved all of that. And so that's the picture, that's the full scaling limit of the double random current model, okay? And now the question is, where is this Ising magnetization field? So, as you remember, the Ising magnetization field could be written as a sum of sign measures of the percolation model. And the percolation model was the dual complement of the double random current. So the Ising magnetization field will live in these sort of spaces between the loops. Because the loops converge to the double random current model, and the Ising magnetization field is the dual thing, which is basically it's a complement. So in the limit, it should live somewhere in these complements of the loops. Okay, the complement of the loops is called the gasket or the carpet of this collection of loops. And we prove exactly that. So we prove, based on all of what I told you, that the Ising magnetization field has a representation of the same type as with the CLE 16/3. So it's a sum of independent point clips times a measure. These measures are now indexed by some clusters in the continuum, and these clusters are the spaces between these loops, basically. So the first cluster will be the gasket or carpet of the CLE4, and the next clusters will be somehow spaces between the blue and the green. Yeah, we proved that. So there are these measures in the continuum which are conformal invariant, and I think we can identify what these measures are exactly, but this is still work in progress. Yes, so what are the difficulties? The difficulty is that the model has no FKG, and that's a very important part of the proofs of these other representations. And the resolution is that it has almost FKG, and that's also based on a paper of Pete and Sasha Glasman. You can write the model as a union of two models which both of them have FKG, but together they are negatively correlated. So you have to work with that, but you can do that if you have smart enough PhD student. And it worked out. So that's the whole story. And yeah, I think so. The paper that will be appearing soon, I hope, will provide a nice tool to study the Ising model in the general case, not only the planar case. So yes, thank you for.